Welcome to Measure Theory. This is a part 1 of a series where I want to give you an introduction into measures and integrals, and where we will prove some interesting results in the end, which are used very often in mathematical topics. The motivation is indeed the famous Lebesgue integral, and to find the Lebesgue integral we need a meaningful notion of a measure. So let's start here with the real line now. This is a real line. We can look at subsets on real line and ask how to measure these subsets. Okay, this is R and this is a subset of real line, and we need to ask to measure this subset. Okay, here. Or in other words, what is the measure of this subset? And this is what measure theory is about. We want to give the subset a meaningful measure of, in other words, a generalized volume. The measure of the subsets. So, in mathematical analysis and in probability theory, a sigma-algebra on a set X is a collection sum of subsets of X that includes X itself, is closed under complement, and is closed under countable unions. So let's realize what we want to say. So we want to give the subsets a meaningful measure, or in other words, a generalized measure, in this case length. So generalized length. The notion of length is what you know from the real line. If you look at intervals, if you have an interval in the real line, if you have an interval here, and let it be A, B, so you would occur this, yes, A to B, and the whole subsets in this, then you would say this has a length of B minus A. The natural question is now what to do if the subset looks more complicated. So here the length is B minus A. So in easy intervals, how can we have then calculate the lengths? They are immediately the measure theory comes in, and maybe also want to deal with a different notion of length. So we want to generalize the measure, the natural length. So maybe depending on the problem, we want to choose different lengths or different definitions of the length. So here different notions of the lengths. Let's look at an abstract set, and we call it just X. Set X. So X, let's just set X is in a set, and for the set we want to measure the volume, generalized volume. of the subset, so we will define a map which we will call later just a measure. Of course, this map should fulfill some roots, but I will talk about this later. First, let's start on the set level, and because we want to measure the subsets of X, it's good to start with the power set of X. The power set of X, and it is just the set of all subsets of X. Px is power set of X, and this is all subsets of X. And I want to give a short reminder that this set, empty set, is also a subset of X. So let's do that example if we have to set with two elements. So let's call the elements just lowercase a and b. Okay, example. Let X be just a and b. Then we can write down the power set. The antiset is always a subset of the set, as I mentioned. So the power set of X is empty set, and X itself, the set itself, also a trivial subset. So these elements A and B are also the subsets, and we constructed the power set of X, and now we can give the definition for measurable sets. Definition. When I say measurable set, you may recognize immediately the idea that maybe we do not have to measure all the subsets we can form, but only some if we have quite an amount of subsets we can and want to measure. Maybe that's good enough for our theory, and therefore we call such sets measurable. And we will later see that we indeed have to do that, because if we want to generalize, even this is a measure given by the length. And let's write the definition. In the sense, we now look at a subset of the power set. Let it be curly A, and this is a subset of a power set Px, and so we'll look at a family of subsets that could be the whole power set. So this could be the whole power set also. So here in general we would have a smaller family of such subsets of X. So keep in mind this fancy A has as element subset of X, and such a collection is called the Sigma-algebra. It fulfills the following words, and this will be three rules. There will be three rules. Keep in mind that this notion of the Sigma-algebra is indeed the important definition in the whole measure theory, and therefore we start with this. Here the elements in the Sigma-algebra will be called the measurable sets. So the first rule and the easiest rule is that here is that the empty set also here in the power set given, and the whole set itself is from the curl A, and the rule B is that A is the element of curl A, and we denote the complement by AC. The AC, the complement of A, is equal to X minus A, so it also should be the element of curl A. Let me show you. Let it be our plane here, and this is A, okay, this is A, and if it's X, here these parts are a complement. If we subtract A from X, we will get a complement. So if a set A is an element of A curly, then a complement of A also should be element of A curly. And the rule C is that AE is element of A, the curly A. Here E is natural. So we get that the union of all AI's should be element of A curly. So Sigma-algebra, these two rules should be satisfied in Sigma-algebra. And let it be again our set X, and X have a subset A, okay. Inside now, assume we have measurable sets inside A. So we have measurable sets here. The union of these measurable sets, let me write it more clearly. Let it be X. Don't look at this. Look at this example. Let it be our set X, and let A be a subset of X. And there are inside of A the measurable sets, the collection of measurable sets, okay. And so given as these squares or rectangles, so this would be A1, for example, A2, A3, and etc. We can form this set, we can form the A from these little subsets. And if we add up all the areas inside, okay, we can form then, you should get out the area of A, and in order to speak, you should get an area of A, and in order to speak of an area or analyze volume of A, we need that the set A is measurable, so it should be an element in a sigma algebra, Okay, and the countable union should also be an element in sigma algebra. If AE is element of sigma algebra, the countable unions should also be elements in sigma algebra. And these are all the words, all systems of subsets with these three words. Now are called sigma-hydra paths to close the definition. I now write down what I told you the whole time. So let's do some examples. The first example is if X is a set from the elements A, B, C, D. One possible sigma algebra on X is what is the power sets of X, empty set itself, and X itself, A, B, C, D. Also, they can be just AB, a set AB, or a set CD. This is one possible sigma algebra on X, where empty set is also included here. In general, a finite algebra is always a sigma algebra. A finite algebra is always a sigma algebra. If A1, A3, A2, A3 is a countable partition of X, let me write. If A1, the set A1, A2, A3, and etc. is a countable portion of X, then the collection of all unions, the collection of all unions of sets in the partition including the empty set, is a sigma algebra, A more useful example is the set of subsets of the real line formed by starting with all open intervals and adding in all countable unions, countable intersections, and relative complements, and continuing this process until the relevant closure properties are achieved. The sigma algebra produced by this process is known as the Borel algebra on the real line, and can also be conceived as the smallest sigma algebra containing all the open sets, or equivalent containing all the closed sets. It's foundational to measure theory, and therefore modern probability theory and the related construction known as the Borel is of the relevance to describe the set theory. Let's look at some examples about sigma algebras. So let a make up B set containing elements 1, 2, and 3. Then F1 is a sigma algebra because it contains empty set and the set itself and also some subsets. But F2, let it be empty set 1, 2, 3, and 1 and 1, 2, 3 is not a sigma algebra. Why not? Since for the subset 1 is from F2, but the component of A, the component of 1, if we subtract 1 from this set, we will get the set 2, 3. Yes, could we find the set 2, 3 here? No. So this is not the complement of A, is not from F2, so F2 is not a sigma algebra. Look at the first example. We denoted 1 is a subset of F1. If we subtract 1 from this set, we will get 2, 3. And here 2, 3, let me know, 2, 3 is a subset. 2, 3 is a subset of F1. 2, 3 is from F1, an element of F1. And we get that if A is from F1, the complement of A is also from F1. But here, A is from F1, but complement is not here. If we write there 1, we should also write 2, 3. And if we write 2, if we write 2 and subtract this, we will get 1, 3. We should also write here 1, 3. If we cancel out 3, we will get 1, 2. Here also should be 1, 2. Then we will get a sigma algebra. But as is clearly seen that here the complement of these sets are not included here. So the F2 is not a sigma algebra. And here is our second example. Let gamma be a real number set. Then if F is the collection of all subsets in R, then F is a sigma algebra. And here is our third example. Let gamma be the natural number set. Then F1, let it be empty set 1, 3, 5, 7, 9, and etc. What is this? This is the odd number sets, yes, and also 2, 4, 6, 8, and etc. even number sets, and N itself is a sigma algebra. Why? Because as we denoted before, the empty set and the set itself are included here, and if we write the even number sets, the odd number sets from N, the complement of odd number sets are even number set, and even number sets also included here. And F2, let it be A from N such that A is countable or a complement is countable. Then F2 is a sigma-algebra. And our third example, let A be a subset of N such that A is finite or the complement of A is finite. This is not a sigma-algebra. Why not? Since the sigma itself is n, which is n, is not included to F3. That was our topic about sigma-algebra. Hope you can understand the examples. If you have any question, please let me know and write it down below in the comments, please. See you in our next video.